Coming back to local filters, there is another extremely important and extremely popular local filter, which is called the median filter, which we're going to describe next. And it's a great filter because it doesn't really blur edges. And although it's a very classical filter, it's still very useful today. So let's observe it. Before we actually describe it, let's see what happens with a real image. We have here an image that has been contaminated with what's called salt and pepper noise. Next week, we're actually going to describe different models of noise a bit better, but salt and pepper is just noise that basically is very strong noise individually added at different pixels. We see it here. This is the result of the local mean filter, what we have seen in the previous videos, just local averaging, in this case a 3x3. You might be able to observe there is some reduction of noise, but not really too much reduction of noise. Here, on the other hand, is the result of a 3x3 median filter. And we see a great result. We don't see blurring, and we actually see that a lot of the noise has been reduced. We could reduce much more noise with a local mean filter, a local average. If we go beyond 3x3, we might go 5x5, 9x9. Remember, by averaging, we are reducing the noise by square of the number of pixels that we are averaging, as we saw in the previous videos. But if we enlarge the neighborhood, we also saw that we are going to start to blur a lot of the details. On the other hand, keeping a 3x3 neighborhood will still get extremely good denoising with the median filter. So what's the median filter? Very simple. What we do is we actually take, let's say if we are working on a 3x3 neighborhood, we basically order the pixels. So we basically order them from the smallest to the largest, and we pick the one in the middle. Okay, so we start putting all the pixels in order, we pick the one in the middle. This is an operation we actually learned in elementary school, and it's an extremely powerful. Replace it by the one in the middle. So for example, if you have pixels which look like this, and one of the pixels is very noisy, when you order them, this one is going to be replaced by one of these values. They're all equal, so it's going to be replaced. It's going to go down. Okay, so the noise is clean, completely clean, without blurring, as we have seen for Gaussian filtering or for mean filtering. It's a very, very simple filter. You order and you pick the one in the middle. You order from the smallest to the largest, you pick the one in the middle. And then you move to the next window. So you basically take a 3x3 window, then you move to the next window, the next window, the next window, and you get this extremely simple filter, the median filter. Before I show you additional examples of the median filter in real time, we're going to actually run MATLAB to do that. Let me just give you one very interesting property of the median filter. We saw in a couple of videos ago that the average filter is reducing this, A minus AI squared. We say the average is the value of A that reduces, that minimizes this, and I'm summing over all the pixels. So I'm going to ask you a question. Can we represent the median filtering in a form like this? A different function, maybe. Sum of certain function of A minus AI. Can we do that? Just think for a while and tell me yes or no if you know the answer of that. So what's the answer to this question? Very interesting. This is the mean. The value of A that minimizes the square error is the mean. What's the median? The median is the value that minimizes the absolute. There is no square here. It's just the absolute difference. It's extremely interesting that by replacing this square by basically nothing, just absolute value, we get the median. Once again, you can prove this. It's a bit more of a difficult proof because when we discuss how to prove this, we say just take derivatives, make the derivative equal to 0, and you're going to find that A is the average of all the AIs. Here, you're not allowed to take derivative because at 0, the absolute value doesn't have a derivative. So the proof is a bit more delicate, but I'm sure that you can do it as a bonus exercise. Don't worry too much about that for now. You can believe me that if you don't want to do the proof by yourself, that the result of minimizing this is the median filter, an extremely interesting operation. For those that are familiar with the area of robust statistics, this is a square error, which is not very robust, and that's why it's blurring. This is a much more robust error, and that's why it's able to completely eliminate noise, like salt and pepper noise, without blurring the rest of the image. The last interesting property I want to mention about the median is in the average, the result doesn't have to be one of the pixels. So for example, if you're averaging 1 and 2, you get 1.5. It's not 1, it's not 2. Okay? When you're averaging, let's say when you're computing the average of a 3 by 3 and you're replacing the middle pixel by the average, you might be replacing the pixel by a value that doesn't show up not in the 3 by 3 window, maybe not even in the whole image. Once again, the average bit of 1 and 2 is 1.5, a new value. On the other hand, when you're doing the median filtering, you're always replacing by one of the values that already exist in the 3 by 3 window. So you're not producing new pixel values. And that's part of what's happening here. And that's a very interesting property by itself. There is no novelty, there is no new values, only those that are already familiar in the neighborhood of the pixel that you're replacing the pixel with the median. Now that we know about the median, now that we know some of the interesting properties of the median, let's just see a few additional examples of the median filter in action. Let's see that in the next video. Thank you.